Okay, folks, so here's a little introduction to structural loads. We're going to focus first on gravity loads and then jump into lateral loads. And this is something that you'll study beforehand. You'll then take a quiz. We'll discuss it a little more in class, and then you'll go right into your assignment or submittal in class and work on that with input from both me and other students if you need or desire that. Okay, so let's talk about load paths. Why do they matter? So this is a house that I went out on this summer. The roof was sagging. It's not super obvious, but when you get up there in person, it's pretty obvious. This little black line here is straight, and you can see these solar supports are not straight. Insurance company wanted to know what was going on. Homeowner wanted to know what to do. Here's some damage. So in the garage ceiling had sagged quite a bit. There's probably 8 inches between the top of that shelf and the old ceiling line. Up in the attic, you can see this portion that's basically torn. Um, so at first I walked around the house, looked at this, wasn't quite sure what was going on. Came up here, looked at it, wasn't quite sure what was going on. And then I saw this picture and everything became clear. So I would like you to look at this picture, these pictures, and take a thought on what's going on. I'll give you a little hint. This wall here sits about here on the ceiling. So I want you guys to give this some thought, and we'll talk more about that in class. Okay, so types of load paths, gravity and lateral. Gravity is typically what we think of in loads. Lateral would be like wind and seismic. It's somewhat equivalent to taking a building, turning it 90 degrees and bolting it to the wall and having it cantilever off. It cantilevers off the ground. Building codes, why do we have them? It gives us a consistent basis to do our designs, so we can say we're following the standard of practice, and if there's a problem, we have at least some leg to stand on as to base our designs. Here's a number of different building codes and material codes. Risk categories. So we put each building into a risk category. Category 1 would be something like a barn. Category 4 would be a hospital. 3 would be schools, theaters, water treatment, that it has a little more societal risk, but not as much as a fire station or a hospital. And then everything else is category 2. So the ice cream shop you go to, or the gym, or a grocery store, those are all Cat 2 buildings, office buildings, whatnot. Okay, so each category is assigned an importance factor, and right now for snow and seismic we apply them separately. For wind, they're built in. Wind is built into the wind speed chart, so we don't do that anymore. Apply a separate factor. Okay, so some dead loads, things that are permanently part of the structure. Um, Maybe do this at your own place where you live or at work and just list some dead loads. What are dead loads in um, the space you live in? All right, densities of different materials. And then this dead load chart will kind of expand on that. So if I have roofing, maybe membrane roofing, it's a pound per square foot. Metal deck, say around 2, and you can look up the actual deck and dial that in, but 1.5 inch B deck is 2 pounds a square, which is common roof deck. Ceiling, gyp board, so sheetrock type, 5 pounds per square foot per inch. It's important to remember that this is per inch. So if I have 5/8 sheetrock on a ceiling, then I'll multiply that number by 5/8. Okay, so you can play around with that. Just different timber framing dead loads, basically some reference info for you guys. Dead loads of CMU walls, so masonry walls. Okay, so when I calc dead loads on a project, I'll just start at the roof, go to the ceiling, or a floor covering and go to the ceiling below that. So in this case, I've got a roof membrane, some type of insulation, some kind of deck, the structure, mechanical, electrical, and plumbing, and gypboard. Don't get too wrapped up around the wheel about accounting for every light. Generally what we do is apply 3 to 5 pounds a square foot to cover those things. In industrial structures, we'll look at it closer because we may have really substantial pipe or duct loads or equipment loads. So we basically come in, I like to list what it is, pounds per foot. Insulations, I have 4 inches times 0.2 pounds a square, gives me 0.8 pounds a square foot. There's the metric equivalent. 2-inch B deck, 2 pounds a square. Structure, 5 to 8 PSFs, pretty common if you want to figure it out yourself. Take your framing layout, what you think the members are going to be, and figure out what the weight per square foot of the framing is. MEP I used 4, and then ceiling, you can see I took 1/2 inch times 5 pounds a square, 2.5 pounds a square foot. All right, so you guys will do that in your load submittal, basically so I can check your loads and make sure you're using things that are in the right ballpark, not too small, not too big. All right, live load. This picture is about 50 pounds a square foot of people. This is 100, so we usually say 100 pounds a square is like an elevator packed full of people. The IBC gives us, and ASCE 7 gives us different live loads for different uses. So if I'm in a hotel, private room, I'm 40 pounds a square. Public rooms and corridors, 100. You can see, imagine in a hotel you could have, if you're just in your room by yourself, not much load. If you're in a room where lots of people could occupy it, it might be pretty substantially loaded. Manufacturing, I would suggest don't use the code values, figure it out with the client and come to a consensus on what loading is going to be there. It could be anywhere from 50 pounds a square foot to 1,000 or 2,000 pounds a square foot. Schools, so you can kind of play around with this. If you have a copy of ASCE 7, you can dig in deeper to these numbers. Okay, rain matters sometimes. Ponding is a phenomenon where the roof gets loaded, it deflects. Additional water can flow into that deflected shape, which causes it to deflect more. More water can fill in, which makes it deflect more. More water comes in, deflects more. More water comes in until it collapses. Usually flat roofs, like on Walmarts, have this type of propensity. So there's 2 ways to deal with it. One is to analyze the deflection and either show that it comes to steady state or collapses. If it collapses, choose bigger members and reanalyze it. The other is to make sure the roof is sloped about 1/4 inch per foot, which then really reduces the likelihood of ponding problems. All right, snow load. We can have a couple types, triangular or uniform from drift. There's a snow map in ASCE 7. You can see for most of Utah here it says CS, which means case study. So in Utah State put together a ground load map. If we do wherever I have these coordinates in, we can fire that up. Have no idea where this is or why it's showing up here. Basically, I can pull the ground snow load out of this Utah State snow load map. Okay, so for different parts of the country, some places are 0 down in Texas. Some are case studies. Some are like big swaths of 20 or 25 or whatever. Okay, ground or flat roof snow load equation. So you have an exposure factor, how much is the wind going to blow off your roof? Thermal factor, how much snow is melting? Your importance factor, then your ground snow load. So depending on what you have, you'll have some reduction usually on your ground snow load when it gets up on your roof due to melting and the wind blowing. Here's the exposure factor. You can kind of get into this based on how it's laid out, like what kind of terrain is around the building. Thermal, I use 1.2 for industrial structures, 1 for like office buildings and homes, and then like a freezer warehouse, then you'd use 1.3. All right, there's a sloped roof equation. Basically, you can take the flat roof load, reduce it by the sloped roof based on if you're warm, cold, and are you slippery or not slippery. So steeper slope buildings, you can shed some snow, reduce the snow load. Drifting, as the wind blows, the snow moves. So as you have changes in vertical changes in geometry, snow will accumulate and increase the loading. So this is something as you're checking drawings or doing a project, anywhere on a roof where you change elevation, we will need to design for additional load or increase the member spacing, which is the same thing. All right, drift heights are calculated based on this equation or in this figure, and then you convert that to a load by multiplying by your snow density. So the drift load SD, this extra load magnitude, is your density times your height. Okay, so retaining walls, basically they're creating steps in the earth. We use these on slope sites all the time. We basically have the pressure of the soil pushing one way and the passive resistance of the soil pushing the other way, because this creates a moment. As you can see, if you sum moments about the centroid of the triangle here, this has an eccentricity. The weight of the soil here pushes back down and keeps it stable. I don't have a free body diagram. When we get into concrete, we'll get way more into retaining walls. As far as soils go, there's the at-rest pressure, active and passive. Active is for a retaining wall like this, that it's unrestrained at the top, and it's about 0.3 to 0.4 times the soil density, the pressure is. So this case of P, or case of active, times gamma. Gamma is the soil density. If this was like a slab or a floor of a building, that would be called at-rest pressure. It's about 50%. And then the passive pressure is 2.5 to 3.5. And the reason that's so high is the wall's getting pushed into that, so the soil really builds up resistance, whereas an active pressure, the top of the wall can rotate, so then you're really also engaging some of the natural cohesion of the soil to stay together. Okay, quick talk, a little chat on deflection requirements. In addition to strength, we want to make sure things aren't sagging so much that they become unfunctional. So you can see this big girder here, it's under load, it sagged quite a bit. There's always dudes with ties and hard hats on test day in a lab for some reason. Anyway, the code gives us some deflection limits. So for a plaster, so gypsum board, sheetrock, you'd be L over 60. That is an L, so it's the span divided by 360. And then you can compare that with the actual deflection of your member due to the loads and the geometry and material of the structure or the member. This little table here for different spans gives you the allowable deflection, so you don't have to calculate it as much. So if I had a 30-foot span, I wanted L over 360, my member can sag an inch in the middle and meet the criteria. For condos, I wouldn't use anything less than L over 480. And then when we're supporting glass and masonry, we use L over 600 quite a bit. All right, how do you calc deflection? Here's some resources. So this equation will give you the max PL cubed over 4080I for a point load. We'll talk more about that in class as we keep going. All right, sometimes it's nice to solve directly for the moment of inertia required for a given loading and deflection criteria, and that's what these equations do. So if I had a uniform load, I wanted L over 480, I knew what my uniform distributed load was, my span, and the elastic modulus, so wood, steel, concrete, whatever, I could calc the moment of inertia required to meet the deflection criteria. In steel design, we do this a lot because beams are typically controlled by deflection, not by strength, at least wide flanges are. So we may start by selecting a beam based on deflection and then check strength later on. Okay, so let's just talk about what E and I are in these equations. I is a geometric stiffness. It's moment of inertia. It's units of inch to the fourth. And it basically says how far away from the centroid of the shape is the material. Further away it is, the stiffer it is, the higher the moment of inertia is. E is modulus of elasticity. It's the material stiffness, usually in kips per inch squared or pounds per inch squared units. And it's a measure of the material stiffness. So aluminums are about half as stiff as steels, woods are way less stiff, concrete is similar, or about a tenth, I think, of steel. Anyway, so when you combine the material stiffness and the geometric stiffness, you can start to calculate deflection. So the E and the I, so material, geometric stiffness. Okay, I think that's it for this video. We'll talk more in class. You'll take a quiz on this, and then we'll go from there.